I'm the director of the San Juan Islands Conservation District. I'm really happy to be co-sponsoring this event tonight with the Madrona Institute and with National Parks. So we're so happy that you can all be here. Dr. Jan Newton has spent a lot of time up here on San Juan Island teaching over at UW Freidinghauser Labs, playing kayaking, and just enjoying the area. So she is very familiar with the San Juans, and she's also done some wonderful talks up here. So some of you may have seen her before. If you haven't, you're in for a treat. She's highly knowledgeable about our oceans and about what's happening there. She's co-director of the University of Washington Center for Ocean Certification, and she also is a professor of oceanography, and just very, also Nanus, your director of Nanus, so she'll probably tell you more about what that is. So we're just really honored to have her here tonight, and I'm so glad that all of you are here as well. So I'm going to have Jan come up now and start the presentation.
Thank you. Thank you so much. I got to check where I am between these two pillars. Thank you so much, Linda, for the warm welcome, and thanks to you all for turning out. You know, literally, I'm just a kid who grew up on the shores of Puget Sound and just love studying it and the ocean. And so that's what we're going to talk about tonight. A little bit about the ocean in general, and then effects from climate and humans. And then if that gets too depressing, I hope I'll leave you with a couple of stories of, I think, where people are making a difference and where I think there's some good energy. So if you're feeling depressed, just kind of hunker down and know that we'll get beyond that. So let's pretend, all right? So let's pretend that we're all space aliens. You probably didn't expect that, did you? And let's pretend that our mission is to land on this planet called Earth and to check it out and to take a picture. So let's pretend we do that. And so what are the odds of the most common sight we're going to see? It's going to be that. It's going to be just ocean and sky. So as you know, the oceans are 2/3 of the planet. How many of you have actually seen this sight where you don't see any land, where all you see is ocean and just sky? Okay, well, come on, you guys are special because you live in the San Juan Islands, but a lot of people don't. So let's say we do this 6 times. We'd see that. We might see this. We might see this, that hard stuff and that green stuff. We might see blue, but with some land. We might see this, although that's actually, if you think of the area of the planet, that's actually a rarer sight. And we'd see this. And so that was 6 slides, and 4 of those slides were just ocean and air. And I think that's so compelling that this is the most common viewscape on the planet, yet a lot of people who live on the land have never even seen that. My goal is that more people understand more about the ocean because it is so important. And I used ocean as the non-plural noun because it is all connected. A lot of people say oceans, but a lot of oceanographers are saying, no, it's really ocean, singular, because it's so connected. All right, so a couple facts about the ocean that I think you can take in. Oceans are big. So I first started teaching in 1991 at Friday Harbor, and we used overhead transparencies, and a lot of you don't even know what those are. But anyway, it's an archaic technology. This is a picture of the very same overhead transparencies from Duxbury's oceanography book. But I love it because it's just so vivid. And so here what we have is degrees north, degrees south, South Pole, North Pole, and over here is millions of square kilometer. And so for the planet, if we clumped all the continents together, so North America, Europe, Asia, South America, Africa, Australia, and Antarctica, that green stuff is all of the land, and the blue are all of the oceans. Pacific, Indian, Atlantic. And so as you can see, as we've been saying from that little photographic tour, that the oceans are the dominant feature on the planet, okay? The other thing is probably something you also know. Oceans are deep, and this is actually known as the hypsographic curve, if you want to know that. But what this is this line right here is sea level. And then this is elevation in meters, going from sea level to 10,000 meters up. And so, you know, what is Everest? 8,000 meters or something like that. And then this is depth over here from 0 to 10,000 meters deep. But there's some interesting facts on here. The mean elevation of land, all the land, is 840 meters above sea level, if we average it all. But the mean depth of the sea is almost 4,000 meters. That's amazing. And so when you average this all out, the land and the sea, the mean Earth sphere depth is actually over 2,000 meters under the sea level. And so I think these facts are just really telling in terms of the dominance of the ocean on our planet, and also how much volume there is, how much energy store there is, how much it is a factor on our planet. So there's two cool things about the ocean. All right, yet, this is pretty interesting. So now, this is from the World Ocean Atlas. This is the number of places where we actually have temperature data at 600 meters below the sea level. All right, and so you can see some ship tracks where you have some volunteer observing ships. You see a lot more in the northern hemisphere. So these are the numbers of observations from 1, 4, 7, 10, 35, 60, 85, 100, 600, 1,000, 5,000, right? So it really amplifies as you get to these hotter colors. But the difference between pink and purple is 1 and 4, so the difference is 3. So anyways, and where it's white, that means 0. So even though we know a lot about the ocean, there's a lot about the ocean that we don't know in terms of our direct observations. This is at 600 meters. Remember, our mean sphere depth is at 2,000 meters. So let's change the picture to 1,100 meters and look at what we have. A lot more white, a lot more purple. So another, just, you know, trying to grasp that the oceans are so vast, and yet some people have said, and I don't know if it's really true or not, but they say that we know more about the far side of the moon than we do about the depths of the oceans. And so clearly, it's as an important feature on the planet, it's something we need to know about. All right. I absolutely love this picture. Isn't it just gorgeous? One of the things I really love is that you can see the atmosphere here. You can see the curve of the Earth. You can see all our beautiful volcanoes and the really cool phytoplankton that's growing here in this upwelling zone, and then the beautiful blue ocean, and then, of course, the clouds. But one of the things that, as an oceanographer, you learn early on is that the ocean, as the fluid on the surface of the Earth, is interacting intimately with another somewhat fluid, although it's gaseous, which is our atmosphere. So you have strong atmosphere-ocean interaction. And so the temperature is exchanged across that air-sea interface, and it's really the patterns in the atmosphere drive the variation in the ocean. The variation in the ocean also affect the variation in the atmosphere. So it's a two-way exchange. And this picture is so beautiful because you really see that atmosphere. Okay, so we're going to talk about climate effects on the ocean. And so I'm sure all of you know El Nino Southern Oscillation is an oscillation between two phases of the Pacific and Equatorial Ocean, between what the El Nino phase is when we have hotter than normal temperatures, and the La Nina when we have cooler than normal temperatures at the equator. And so for a lot of the slides that I'm going to show you, we're going to talk about anomalies. And so average is going to be whatever is here at 0, and then positive anomaly is going to be in one direction, typically red, and negative is going to be in the other direction, typically blue. All right, so we know that, and we know that it oscillates and that it kind of bumps up and down, and it's not real regular. But the thing that's very important is the effect that it has on an ecosystem. So now what we're going to do is look at El Niños and La Niñas on the side. And so This is normal conditions. You see that we have this convection cell. And what you're looking at here is the thermocline. So we're looking at the edge of the ocean. And the thermocline is where the temperature gradient changes the quickest. Okay, so this top layer has a lot of contact with the atmosphere, and so it's warm. This bottom layer doesn't so much, it's cold, and the thermocline is that gradient between it. And it's sloping, and there's so much more oceanography I'd love to teach you, but I don't have time. But anyways, so this thermocline tilts, but in any case, this is quote unquote normal. And then during El Nino, the change in the pressure cell, the change in the trade winds, but big importance for the ocean, because this is an ocean talk, is the change in the thermocline. Okay, you see that it's depressed. It's shifted down instead of where it was up here where we have upwelling. And then in La Nina, it's just the opposite. It shifts really high up. So why would that matter? So I've just been talking about the difference in temperature from warm to cool. But deep waters have a lot of nutrients. Surface waters don't have much nutrients because the nutrients get consumed by the phytoplankton that lives up near the sunlight. And so here is sort of the counterpart. So when we have normal conditions, or when we have La Nina conditions, we get a big pumping of nutrients up to the surface. So what happens? We get a lot of phytoplankton. What happens? Those get eaten by zooplankton. Those get eaten by fish. Those get eaten by mammals. Those get eaten by seabirds. All right, when we have an El Nino, this thermocline is depressed, it comes down, and the nutrients don't penetrate up to the surface, and so you have fewer phytoplankton, fewer fish, and you have some hatchery failures for the seabirds and marine mammal populations. So this is a natural oscillation, and it has definitely been recorded for centuries in terms of what's going on. But the point is that atmosphere, ocean, and biology, they're all connected. So that's the really important point. All right, so La Nina, El Nino isn't the only climate pattern we have. We also have something called the Pacific Decadal Oscillation. And this is another climate pattern. And each one of these climate patterns, explains somewhere between 10 and 20% of the variation that we see. This one, as you can see from these index values, they oscillate between positive and negative on much longer time scales. That's why they called it a decadal oscillation, because sometimes the periods that it's positive is decades. All right, as opposed to something that's more interannual with El Nino. And so similarly, we're not going to go into as much detail, but similarly, the Pacific Decadal Oscillation has been linked to the survival or less of salmon and other organisms. And so here you see the PDO, and you can see positive, negative, positive. And now these are different kinds of salmon, sockeye, pink. These are from Alaska, and then these are the Columbia River spring Chinook. And what's really interesting is that the Alaskan fish are kind of really responding in phase to these negative, whereas the Columbia River Chinook are really responding to this negative, did I say negative? I meant to say positive, negative, phase of the PDO. And there's reasons for this. And again, we don't have time to go into it, but the point is the atmosphere, the ocean, the biology are connected, and they're operating together, and they affect one another. And so we have these natural cycles, these climate cycles that are going on. And there's teleconnections to the land. Here's El Nino and rainfall. Here's PDO and precipitation anomaly. And the point of this slide is to hone in that point of the connections, but also to say that it's not the same on the planet. What happens? You have dry, wet, dry, wet. Also, here just within the United States, dry, wet, wet, dry. So there's very strong interregional variability in terms of how these climate patterns are manifest, and that variability is manifest. So it's getting a little complicated, right? But it's something that definitely can make a big difference to salmon harvestability, crops, etc. So back to my favorite picture. Well, yeah, this is the part where we've got to talk about what else is happening in our atmosphere. So it isn't just the natural variability. Humans are changing actively the content of CO2 in the atmosphere, and that's making some big changes. So we are affecting what's in our overlying air masses. And how are we doing that? This is from the IPCC. The anthropogenic increases in CO2 are 90% from fossil fuel combustion, and then 10% from deforestation. And so hopefully, you know, photosynthesis happens, and what do photosynthesizers do? They take up CO2, right? And when you cut down the things that take up CO2, that means you have more CO2 in your reserve. So we have this excess CO2. Where does it go? Well, about half of it accumulates in the atmosphere. About a quarter to a third is taken up by the uncut land plants, and about a quarter to a third is actually taken up actively into the oceans. Okay, so there's your math. And here is a partitioning of the emissions. It's really what I showed you in the previous slide, but now showing you versus time. So this starts in 1750 and the Industrial Revolution and goes on into the 2000s. All right, and so what's striking, of course, is the steady increase, but the change in the rate of that increase. And this is something you probably know. And so this blue one is the ocean sink from the atmosphere. All right, so what are the consequences to the ocean? Well, so here, or what are the consequences of the planet? So here is the CO2, this black line, and here now we're talking temperature anomalies. So here's our 0 line, and anything that's blue means cooler than normal for the base period. So we've averaged the entire 20th century. And so the whole, from the start to the end of the 20th century. So the middle really should be the middle. So the cooler part of the 20th century is going to show blue, and the warmer part of the 20th century is going to show warm. The problem here is that the warm part is all at one end. It isn't oscillating like you saw with the PDO or the ENSO. It is very directional, and it is very much at the same slope as the CO2 increase. So we know climate change from these records, and it's extremely well documented, and this is the magnitude of it. And so we're talking here, this is in Celsius, so 0.9 degrees Celsius is going to be a larger number in Fahrenheit, if that's what you're used to. All right, so here are some striking patterns, and I'm going to walk to the other side just because I like to spice it up. Okay, so I like to drive the cameraman wild. So this is 2016 annual mean relative to the mean from 1880 to 1920. Okay, so basically last year relative to years that are a long time ago. And here's our anomalies. And so white is basically from negative to positive 0.2. So the warm colors are warmer than average, the cool colors are cooler than average. And so that's for 2016. And you can see it's pretty compelling in terms of how warm 2016. From the same paper that was published, here are the rates of temperature anomaly. Well, it's not the rates, it's the anomaly, but from that you can see this increase in both over the land and over the ocean. Okay, so again, very compelling values in terms of that the oceans are warming up. All right, so you remember that intimate connection between ocean conditions and biology. And so here, there could be plenty of papers that I would show you, but here is one. Extreme climatic event alters marine ecosystem structure in a global biodiversity hotspot. This was published out of Australia. And they conclude that extreme climatic events are key drivers of biodiversity patterns, and that the frequency and intensity of such episodes have major implications for predictive models of species distributions as well as ecosystem structure. So in this paper, they really developed that. And this event that was in Australia was a large one, 7,000 acres of dead mangroves in Australia. And we all know the importance of mangroves as an ecosystem type, right? What is compelling to me, and it's compelling to me doing it on a night like tonight, is that this term, marine heat wave, okay? So right now, we are having a heat wave, right? But the term marine heat wave wasn't in the literature until 2011, and now there's a lot of papers about marine heat waves. So are heat waves caused by anthropogenic climate change? Well, we've had climate change, or we've had heat waves over recorded history, but the frequency, duration, if the whole thing is warming, then the chances that any event is going to be a hot one is just that much more. So too with the oceans. So now this is some more data of the satellite-derived ocean temperatures. And again, it's anomaly. So this is 0 is white, this is warmer, this is cooler. And this is January 2013, and there's Australia, and you see that there was an awful lot of warmer than average temperatures when those mangrove deaths were occurring. Now, this is January of 2013. Let's fast forward to January of 2014, and another marine heat wave came into our area. Does anybody know what that was called? The blob, yes. Nick Bond at the University of Washington nicknamed it that. And you can see it has a very large footprint, and it persisted, and it came into the Salish Sea, and some of its heat is still within the Salish Sea because we have these sills that mix the water and are kind of retentive, so not all of the ocean water that comes in goes directly out. Some of it is retained, and so this was a big fingerprint. So that's January 2014, now January 2016, and we have this very large El Nino event. All right, so now we've got a couple of heat waves, we've got El Nino, and a big question you might be wondering, so if natural climate variation and anthropogenic climate change are happening at the same time, how can we tell the difference? And there's a couple answers that I would give to that. One is that we know the patterns of the natural variability, and we can also relate the mechanisms of the increase, like you saw with the CO2. But another answer to this is it sort of doesn't matter. It doesn't matter to that fish that's swimming in the sea. They just know that it's hot. They know that it's harder to find the food. They know that it's harder to reproduce. And so that's where the important study comes, is trying to understand how the resources that we depend on are being affected by the conditions that we have, and then perhaps understanding other pressures that might be affecting them. Okay, so I was at a conference with Dick Feely, who is a NOAA oceanographer from the Pacific Marine Environmental Lab, and he gave a great lecture on temperature change in OA, and I stole his slides. So these key findings are Dick's and his words, but I agree. So globally, annually, average surface air temperature has increased by about 1.5 degrees Fahrenheit over the last 135 years. Human-emitted greenhouse gases are responsible for most of the Earth's temperature increase since 1951. And land temperatures remain at historic highs while ocean temperatures continue to climb. Okay, so that's temperature. Now let's think about the other impact that we might have from CO2 emissions. And remember, this CO2 that going into the oceans, that's actually in a way a good thing, because if it wasn't sinking into the ocean, we would have more CO2 in our atmosphere. We would feel the effects from those temperature increases even more. But there is the other sink for CO2 causes another problem, and that's ocean acidification. So some people term that the other CO2 problem. So because this absorption of CO2 into the ocean has occurred, it causes this process called ocean acidification. I'm not going to go into the nitty-gritty of the chemistry, but basically, if you are looking for a definition you can remember, CO2 absorbed by seawater is going to increase the CO2 in the seawater, but it doesn't stay as CO2. It reacts, it forms an acid, carbonic acid, but then that dissociates. So don't try to go there. Just remember that it changes the water chemistry. And it does two things. It reduces the pH and it reduces the carbonate levels in the ocean. And we'll talk a little bit about each of those, pH and carbonate. All right, so CO2 absorbed by seawater changes water chemistry. Does two things, reduces pH, reduces carbonate. All right, so here are some data from different global ocean basins, Bermuda, Canary Islands, and Hawaii. And the black line is the atmospheric increase in CO2. That's actually taken from Hawaii, the Mauna Loa station. The green and blue and gold are PCO2, the partial pressure of CO2. It's just one way of measuring a concentration in the seawater. And you can see the black is the atmospheric, and those other colors are in seawater. And so they're increasing at the same rate, and moreover, all the ocean basins are doing it similarly. So this is a global condition. And at the same time as the CO2 is increasing, the pH decreases and the carbonate decreases. And they all have that same consistent slope. All right, so we have a global condition. It's known as ocean acidification. The CO2 from the atmosphere increasing the CO2 in the seawater, the pH declines and the carbonate declines. All right, so now let me back up here. Let's look at this scale. It's going from 8.05 to 8.20, and you might think, well, what's a few decimal places among friends, right? Well, pH is on a logarithmic scale, so like Richter scale for earthquakes. So there's a big difference between those decimal places. So a pH change of 1 unit means a 10-fold change of acidity. All right. So the pH change from ocean acidification is about 0.1 pH units. That's a 30% change in acidity. So if you have a 30% change in your bank account, you notice that, right? All right, so small changes in pH units mean much larger changes in acidity. And one of the things I want to really reinforce is that seawater is basic. Seawater is in the 8, sometimes the high 7s or mid 7s you can find in estuaries, but seawater is not acidic. And a lot of people say like, ooh, acidic seas. Well, they're not acidic, so don't worry about, oh, if I touch my toe and then it's going to be acidic. I really doubt that we're going to be on this side. We call it acidification because it's in that direction, just like when you have a really strong cold snap and things freeze and it warms up to 34 degrees Fahrenheit. 34 is not warm, but it's warmed up, right? So that's the same way that we're using this term acidification. So that's just a pitfall a lot of people fall into. But in any case, so that's a little bit about pH. Let's now talk about carbonate. Okay, you probably have heard about calcium carbonate, right? That's shells, oyster shells, clam shells, crab shells. So why does declining carbonate matter? Well, when an oyster, for instance, or any calcifying organism is young, it starts out really microscopic, and it's got to start laying down those calcium carbonate layers. And so these are all little tiny oyster larvae. They're called dehinge when they're in this stage for obvious reasons. And so these two, this is day 1, day 4. These two grew up in seawater that had sufficient carbonate. These two did not, and they had less carbonate. The form of calcium carbonate that they're laying down is actually called aragonite. So if you hear people talking about aragonite, you know what that means. Calcite is another form, but they're both forms of calcium carbonate, and you need the carbonate in order to make that shell. And a lot of times people abbreviate it by the saturation state of either of those things, and they use a little term called omega. And so here's something for your next cocktail party. Just throw out the term, the saturation state of aragonite. You know, but so that's a little bit disarming because people don't know what that means, but it simply means is there sufficient carbonate or less carbonate, all right? Okay, so how does CO2 in water affect marine life? Well, it's complicated because first of all, we've got different things that are changing. CO2 is increasing, carbonate is decreasing, pH is decreasing. And to an organism, all of those have different implications. This, as we mentioned, is really important for calcifying organisms, decrease in shellfish calcification. But not all organisms in the sea are calcifiers. Some things are affected by pH, some things are affected by how much CO2 or bicarbonate there is in the system. And you can even cause the photosynthetic plants to increase their photosynthesis, which would be seemingly a good thing when you have more CO2 in the water. But we're also seeing changes in physiology and very complex changes like the ability of a fish to smell its predator, which is changing because of the seawater chemistry changes. So it gets really complicated fast, and there's a lot of effort is going into understanding these biological effects in light of ocean acidification. But then any organism in the sea isn't just feeling the effects of ocean acidification alone. We've already talked about temperature that's increasing. We haven't talked about decreasing oxygen, but we will in just a bit. And then there's all these other things that humans are doing to the global ocean. And so when you're stressed from these things can be that much worse. So this is very important. You know, a lot of laboratory experiments go on, but it's also very important to study it in the environment that the organisms live in and the combination of those two. All right, so wrapping up ocean acidification. So here is a picture of this scale of pH, 7.1, 8.3. In 1850, most of the oceans looked pretty much on the blue end of the scale, the higher pH. In 2100, which we're not there yet, of course, but this is the projection, and so much more into these yellow areas. And so those are the projections based on CO2 emissions, the chemistry that we know is occurring. All right, so to wrap this up, approximately 20% of the CO2 generated by human activities since the Industrial Revolution has wound up in the oceans. Ocean acidity has increased by 30%, as we mentioned. And the current rate, this is the thing that's the stickler, the current rate is nearly 10 times faster than any period in the past 50 million years. So yes, CO2 on the planet has changed with ice age epochs and that sort of thing, but past 50 million years, we are 10 times faster than that rate. And I'm older than a lot of people in the audience, but I always remember that I Love Lucy episode where she's on that assembly line and she's making the chocolates, right? And she's doing pretty good, and then all of a sudden they turn up the rate of the conveyor belt and all heck breaks loose because she just can't keep up. So this is the thing we really need to worry about. It's not that things are not going to change, because they are, but it's the rate at which they change, because the rate allows people and species to adapt, and so that's the important part. All right, so back to this picture. The important thing here, too, is that not all of these colors are homogeneous. There's early vulnerability, particularly in the polar areas because the water is colder and because there's more freshwater influence. And in tropical areas, it has to do with some of the upwelling and some of the vulnerability of the corals there. But also, I mentioned upwelling. Along the coasts of the continents, there's due to the wind stress that causes the advection, the pulling away of the surface ocean waters and the deep waters coming up. That happens off of our coast, the Pacific coast here of North America, and that's where we live. So here is the picture of upwelling happening. Wind stress when it's equatorward displaces due to the Earth's rotation the waters offshore, and waters upwell from underneath. In our area, this happens mostly in summer, and in winter we have the opposite effect. Okay, so now we've been talking a lot about CO2, and so why does upwelling sort of matter to this whole ocean acidification situation? Well, photosynthesis consumes CO2 at the surface, right? Photosynthesis, but respiration releases it near the bottom. And so when you have the upwelled waters coming up, there's a lot of CO2 in this, and so that's coming up to the surface. So now you've got that anthropogenic signal, but you also are bringing up naturally high CO2 waters, okay? And they mix together. And so we've been talking a lot about CO2, but we said that deep waters have high CO2, they have high nutrients. What else do they have? We didn't talk about oxygen. And so is the oxygen going to be high or low down here? Yep, there was my hint. Yes. And so that's the interesting thing about CO2 and hypoxia is when we have high CO2, we also have low oxygen. And so here's an interesting graphic by Li-King Zhang comparing the west coast of the U.S. to the east coast of the U.S. So you heard all this stuff about, oyster growers on the Pacific coast, and why are we hearing it? Is this because, Seattle is liberal? Well, no, it's not. It's because our oceanography is very different on the west coast versus the east coast. So let me explain that to you. So this gray is the seabed on the west coast. We have very narrow continental shelves. On the east coast, it's very broad, and there's really cool geological reasons, but we don't have time for that. So anyways, so that's just the structure of the continental shelf in gray. Then what these colors are is salinity, oxygen, and this corrosivity. It's actually the saturation state of aragonite, or that little omega term. And so so more corrosive, less oxygen, more oxygen, fresher water, saltier water. All right, so on the west coast, all of these colors bend upwards. Okay, so what is driving that variability? Upwelling. All right, so here out off away from the coast, it's all layered like it should be. But as you get towards the coast, because the winds have been blowing this way and the water gets pushed this way, this upwelled water comes up. And so now we have more corrosive, lower oxygen, and higher salinity waters at the surface. Now, on the East Coast, that same phenomenon doesn't happen the same way and in the same season. And so you maintain this salinity gradient with the lower salinities next to the shoreline, the lower oxygen offshore. But look at this corrosivity. You actually see some blue, some lower saturation state waters next to the coastline. And that's really influenced a lot by the salinity and by the runoff from the land. So this is not to say that the East Coast doesn't have any issues with ocean acidification. I know some of the shellfish growers in Maine and some of those areas do see some of this issue cropping up. But it's a different mechanism than on the West Coast. And that is really important that we understand the mechanism, because then we can understand something about its predictability and how to adapt to it. Okay. So Washington water is particularly vulnerable to ocean acidification, and when you have ocean acidification legends like Dick Feely out there measuring the conditions on the West Coast and finding that these values were lower than what they thought earlier, then thinking about, well, why would that be? And so we've talked about upwelling, we've talked about decay of matter, and we've talked about runoff of nutrients and organic carbon that just feed that decomposition and therefore create more CO2. So it's all of these things working together, but if it wasn't the anthropogenic signal on top of that, you wouldn't be pushing over the threshold as often. Okay, so what we found is that in the early to middle 2000s, many of the shellfish hatcheries were actually having problems settling their larvae. Shellfish hatcheries work, so if you're going to grow shellfish, at least here in Washington State, you can do it two ways. One is you rely on a natural set, and so you just go out and you harvest whatever is there. Or if you're really going to be in commercial business, you would get seed, which are these little tiny baby oysters, and they would probably be a little bit bigger than that. And you would actually go out and seed your beach, just the same way that a farmer would seed the fields. And so you have hatcheries, and Taylor Shellfish up here in Dabob Bay and Whiskey Creek down in Netarts are major hatcheries that then supply the seed to all of the shellfish growers who then go out and seed their beaches. And they were finding failure in this production at their hatcheries. And it was very puzzling, and they tried to figure out what was it due to. And then working with oceanographers at OSU and at UW, they realized it had a lot to do with the ocean chemistry. So that's really how we found out a lot about how much the anthropogenic signal was making the difference in the Pacific Northwest. All right, so global condition, but local effects. And so here is Bill Dewey, and here's former Governor Christine Gregoire, and I just love this picture. It's just like, look, it doesn't work the same. And she's just going like, I think I need to do something about this. And so she did. She organized some people to ponder what is the condition and are we contributing to it as well. And so she organized a blue ribbon panel in Washington State to make a scientific summary of what was going on, and then to work together as a panel, scientists, decision makers, industry people, the tribes, the agencies, knowledge to action to make recommendations on what we should do. And so this was in 2012. And then the legislature, following that, did two things. They established a Marine Resource Advisory Council that are decision makers and kind of that same composite that are keeping the finger on the pulse of what's going on in terms of ocean acidification and the recommendations. They established this center at UW, and it's been my honor to, along with Terry Klinger, who spends a lot of time up here in the islands, to co-direct that. And they actually directed us to implement actions from the Blue Ribbon Panel recommendations. Okay, so what are we doing? We're making some measures. We're out there with NOAA and making measurements on buoys off the coast and in Puget Sound. There's the atmospheric CO2, and you can see, just even with this short record from 2009, you can see it increasing. The atmospheric median is increasing with time. This bottom panel is CO2 in seawater, and that's not as easy to interpret. There's some really interesting patterns, though, differences between what we see offshore and what we see within Puget Sound. And it has a lot to do with the mechanisms, the oceanography. This dips down during summer because of the upwelling. This is so high in the winter because of the mixing in Puget Sound and because of the strong uptake by phytoplankton in summer. So there's less variability. But what's sobering is this sentence by Simone Allen is that atmospheric measurements in Hood Canal reflect CO2 values that are enriched and rising faster than both coastal moorings and globally averaged marine surface air CO2. So what that's saying is when you compare this growth rate off of La Push to what's happening within the Salish Sea, this is growing at a faster rate compared to offshore and compared to the global average. And that is likely due to cars and other emissions. So we've been looking at this corrosivity in surface waters, in bottom waters, in different seasons, and I don't have time to go into it, but what you see on this scale is a lot of different colors, right? You see areas where it's in the bad area. Red is always bad when it comes to oceanography data. And so you see some hot spots, Lower Hood Canal and Whidbey Basin. But you see a big difference in where you are regionally, and you see a big difference between the surface and the depth. And what we're trying to understand are what are those patterns, and then also what biological effects could those be driving. So at a subset of these stations, and also some that aren't shown on this plot, but up in the San Juans, up in San Juan Channel, and then out here in the Strait, we're taking not only the seawater chemistry data, but also plankton data, and looking at the base of the food web at what are the changes. One of the species we're looking at is this little critter known as a pteropod, and it's microscopic. It's whorled shell, but it's a calcifying organism. This is aragonite, and in corrosive seawater, it starts to pit, and if it gets really bad, then you start to get holes. And so we're looking at the patterns in terms of whether there's no dissolution or how severe that dissolution is, and then looking at what patterns we see within the Salish Sea, and hoping to use these as indicators. Now, we know there's a lot of natural processes that make these waters more corrosive, but again, it's that threshold, and so how close are you to pushing organisms over that? Another thing that we're doing is working with some brilliant people who are able to take the processes that go on in nature and make those into mathematical equations and computer models that then can replicate those processes and make forecasts of conditions. So this is a computer model. It's known as Live Ocean. Where is it? Live Ocean. Right there, Live Ocean. And you see aragonite saturation state. And this is, I made this slide yesterday, and I made it so that the picture that you would see is the 3rd of August at 7 o'clock. And it's 7:25, but anyway, so this is the forecast of aragonite saturation state that Parker McCready, Samantha Sidlecki at the University of Washington have been producing through this Live Ocean forecast. This is work that the center is funding, channeling funds from the state legislature to these scientists, and then the output is on the website known as NANOOS, which is an ocean observing system, and I'll tell you a little bit about that in a bit. But in this next biennium, we're going to have model output for inside the Salish Sea. So this will be very exciting and hopefully a tool that shellfish growers can use to adapt. Okay, so a little plug for the center, find us online. And then there's other sorts of issues. We've been talking about temperature, ocean acidification. We had a very big harmful algal bloom, and if you look at the summary that's also posted on this NANOOS website that I'm going to tell you about in just a little bit, there were the conditions of both high temperatures and more CO2 that led to more toxic algal bloom cells. So some of these are synergistic effects. So that's something we want to keep an eye on as well. And then, of course, there were a lot of impacts from this coastwide bloom, which was one of the largest blooms, harmful algal blooms, contiguous on record. All right, so major conclusions. The ocean's warming and acidifying rapidly. Many species are and will be sensitive to warming and acidification. Impacts of warming and acidification can transfer through food webs. Other stressors can exacerbate response to warming and acidification, and economic consequences of warming and acidification are significant. So now I guarantee you I got you to that part where you're feeling like, ugh, you know, this is not good stuff. And so as I promised, I think there's a very pivotal paper that was published a bit ago, which is contrasting futures for ocean and society from different anthropogenic CO2 emission scenarios. This was published in 2015 by the cast of characters you see there. But what I think is so important about this is contrasting futures. Change is inevitable. Our oceans are changing. But which future do you want to have? And so here what they did is they looked for 2100. We could have a temperature change of this much or that much, 1.2 degrees Celsius or 3.2 degrees. You can have a change in pH of 1.14 units or 0.4 units. A change in sea level rise of 0.6 meters or almost 0.9 meters. And it has to do with which emission scenario we choose, and that is a choice. So in this scenario, this is the risk of impact to all of these organisms and these ecosystems. In the business as usual scenario, this is the risk, and you can see on this risk impact, undetectable is white, and then moderate is yellow, red is high, and purple is very high. And so very high is really dominant over here, and moderate is very dominant over there. So I think that, you know, when we see these time series, it can just be so overwhelming. You almost feel like, well, okay, you know, what's left to do? But that's a big difference to live in this world versus that world. And I think that's an important thing to really recognize, that these are measurable differences, and it makes a big difference. And so here is just, I'm going to skip over this. And then, of course, these regional changes in terms of the biology are going to be very different depending on where you are on the planet. So whether you need to grow oysters, whether you need to caretake the earth, you need to make decisions, and for that we need information. So my final plug is just to say that we need to be making sure that we continue to collect the data. This is this ocean observing system in the United States. It's called the Integrated Ocean Observing System, and it's regionally distributed in things called regional associations to do all of these things, to engage with local stakeholders, and to assure consistent national capability, and NANUS is one of them. And I've been hinting on NANUS all night long, but I want to make sure that you know that this is an area where you can go to see ocean data, to see forecast models. And so here's what a shellfish grower said: putting a buoy in the water is like putting headlights on a car. It helps us see what's changing water conditions in real time. And so we've been working with shellfish growers, we've been working with maritime operators, et cetera, to get ocean information to people's hands so that they can make good decisions. And the shellfish growers are kind of on the front line of these changes in the corrosiveness of seawater. So they need good sensing equipment. Burke Hales is an OSU professor who made this machine known as a Burkolator, and it's a very sophisticated contraption that measures the variables, that allows them to actually calculate that aragonite saturation state. A NOAA-funded project to all of these regional associations is developing a lower cost and more versatile sensor. And we're doing it by working with a regional association and a grower in Southern California, Central California, Alaska, Washington, and Oregon. And those are the growers, but we're combining those with scientists who are working in partnership on this, and then having centralized QA from NOAA, and making the data available on a portal, which is linked to NANUS, and so that the growers can look at this on their smartphones and in real time and make decisions. And this is going to help both shellfish operations as well as the science. So here's the aragonite saturation state in Southern California, Carlsbad Aqua Farm. Here it is for the same time period up in Alaska. And if I go back and forth, you can see that there's there's a big difference in that record. This looks like there's a tidal influence. This looks like there isn't. And so the more we know about these things, the more we can adapt. Okay, so that's just good knowledge. And so making a difference, and here are some really cool quotes, but saying that the current generation of shellfish farmer is reliant upon data that we're able to generate and then make available at no charge and readily accessible. So global condition, local effects, but each one of these, whether you're on the shoreline in Washington, Fiji, Caribbean, or New Zealand, it's different organisms, different ecosystem, different effects, different local effects. And I know I'm kind of talking too long, but I want to say one more thing, and then I'm going to shut up because I do want your questions, is to say that what we're doing is not just organizing in Washington, not just nationally, but globally. And so there's a global ocean observing network that's been set up as a partnership to document the status and progress of ocean acidification, its impacts and support forecasts. And here, 330 scientists from 67 countries are participating in it to date. Well, to an old date, so probably more now. There's a picture of our most recent meeting, which was down in Hobart, Tasmania, Australia. And you can see a good mix of nationalities. And then that same type of data portal, but now you're looking on a global scale. So integration from local and all the way to global. So that is what I wanted to say. The two positive messages is, one, be aware the difference that those emission scenarios are making in terms of how that is making a difference. The other is that we need to really coordinate so we have access to that data so it can influence decisions, whether that's growing oysters or figuring out areas to restore or coral reefs or whatever. And so last slide. We live with a changing ocean. Greatest feature on the planet. Ocean lies at and under an interface with the atmospheric processes that affect its character. But human activity is also doing that, and greater understanding of the ocean aids our ability to adapt to future conditions. So with that, I'll say thank you.